next speaker is Chen from National Yang University. Hair stem cell and regeneration.
Thank you for being part of the discussion. First of all, I want to thank for the meeting committee to invite me to have a chance to share what I've done about hair regeneration. Why hair regeneration is so important? I think alopecia will not kill someone, but alopecia destroy your life, right? We take example for this. Charming Prince William, very charming, and now still charming, but both charming Prince, I think, are a little bit sad. So I don't think that's his problem, because I think escape of the European Union with a lot of stress. So I think escape of hair, that's what happens here. So what I'm doing is that if we can identify how to regenerate hair, we can restore its charming again. So about the hair, we always talking about the stem cell. Because hair is a good model, they can evaluate the stem cell biology, because it can recycling all the time within all the our lives. So I think it's a great model to study about the stem cells. But what a stem cell is? The stem cell is a hope or a disaster in the future. I think we got to discuss about that more. We all know that element 3, we see that we can all grow the limbs back. We know the killing the bad guys all grow the limbs back very well, like salamander, right? So I think it's amazing that we're using stem cell to do this way. But come on, we are dermatologists. We don't have to go all the way this way. We just want to grow our hair back. That's what we did. So if we can evaluate how the stem cell be regulated, I think it's better for us to understand it more and regrow the hair. So how do we do it nowadays for a dermatologist as me? So first of all, we're using minoxidil. I think minoxidil is now we're using available, but not very effective for everyone. We have a propecia for AGA or something, but the problem is that we only treat AGA, but the hair loss of female pattern or something like alopecia areata or any kind of alopecia, we cannot treat like this. And also they have some maybe post-financial syndrome or something. Okay, we also have some kind of, the glaucoma solution, right? They can give you an eyelash to grow longer, and I think now we have things called lattice, because we add some more eyelashes or something, so that can give you a 7 times more price. I think that's a big fortune. The same solution, but because of this rush, so 7 times more price in Taiwan. So I recommend to use this, it's cheaper. So now we know that the commercial outside, we can see comb hair, we can comb a hair or using the head to wear it, or even the hair perming, we're using these kind of things at home, like a hair perming, and we can grow a hair. And also we get astronauts. I think some study have done about the plasma-rich plasma PRP injection. It seems not really convinced me that it's really effective, but I think they claim its effectiveness, but after the follow-up for 1 year, some hair loss again, so they did not permanently to maintain your hair growth. So why it's so hard to grow the hair back? Because I think it's 3D structure, and component have 2 germ layers, epithelial part, ectodermal part, and the mesenchyme part. So that's why to grow hair is so difficult. So if you want to resolve these questions, I think we ought to go back to the basic science or research. We all know that from Induce lab, they do a lot of great job in the stem cell regulation. In the past, they always identify the stem cell, do popular and everything. They identify that niche is very important to regulate how stem cell activate. But and also the Greco lab has shown that two-step of the hair regeneration. But it's not that easy to just regulate stem cell by only the niche or microenvironment. A couple years ago, Dr. Cheng have identified that not only the intrafollicle, but extrafollicle also have a lot of signal to regulate the hair stem cells. And also, when I joined the lab, we identify this kind of cellular automatic framework. We identify that maybe the cell is not alone, or hair follicle is not alone. He worked with surrounding hair follicles to coordinate together to form the hair wave. that they can regenerate together or regress together. So I think that's the idea that we can show if we can manipulate the environment and not just identify, just focus on the stem cell, the easier. So that's a physiological condition. The hair is very busy that not only regulate by intrinsic factors like growth factor by wind or growth factor or inhibitor factor here, but also without the outside hair follicle, we also have sometimes signals can regulate the stem cells. So I think we have a couple ways to approach the hair regeneration. First, the physiological cycling. We know the hair can cycling through the whole life, but I think that's not efficient because we will hair loss because of aging, because any kind of physical factor, another factor will affect it, or a hormone factor will hair loss. So I think that's not a great way to get our physiological regulation. Second, we know from this meeting, we found a lot of tissue engineering. They engineering the bio or hair follicles, like separate the dermal papilla, the mesenchyme part, epithelial part, everything combined together, and then also they can control the dermal papilla to do that. In the past, we know that when the dermal papilla is cultured, they lost their progeny. They cannot regenerate well. So now a lot of way to go through it. This Dr. Soren Lin in Taiwan University, he identified maybe they can culture it for 70 generations because using a membrane to maintain the progeny. So they can induce hair regeneration. They also can control the size to induce the hair follicles. But the problem is that they can only induce the embryonic epithelia or the keratinocyte. They cannot induce adult keratinocyte. Even nowadays, we can see a lot of talk during this meeting. We found that they can only induce that kind of immature or the very early young stage of keratinocytes, not adult stage. So that's a problem. Another great job doing by the Dr. Corsarelis a couple of years ago, they find out de novo wound regeneration. Dr. Ito has showed that we can do in this way to neogenesis of hair follicles. But I think ideally it's not that can use on the human. We cannot cut the big wound on the human to let one waiting for the hair follicle reform. But I think we can get some concept ideas from this kind of models of something. So another way is that possible is tissue engineering, as that Dr. Wagner has just showed that we have done that before. DDD has shown that finally we digest the mesenchyme part, epithelial part to combine together. Then we can form the hair nicely to form whatever you have, the happy face or something, but still the problem, we're using the embryonic status of epithelium, and then also they will have ethics issue. We cannot take the embryonic baby to do this way. So is that possible, the reprogramming problem doing this way, that Yamanaka way? I think a lot of researchers in this meeting, they have shown maybe we can use IPS, we can use any kind of stem cells. We push all the way from differentiated state to undifferentiated stage. So when adult keratinocyte cannot be reduced, okay, we can reprogram it back to the very embryonic status, and also mesenchyme, we using the fibroblast, as we show. And Naomi had showed a couple of days ago that about the Sony hedgehog, maybe they can form fibroblast back to the dermal papilla. I think that's ideally we can combine these two. Another problem is that in this situation, the efficiency maybe not that high, and then we got to use a lot of cells to do that, and we got to concern about the cancer change or molecular change or cell differentiation change as a problem, and also aging. Aging affect our hair huge, because I think the aging is a problem that a couple of years ago, I think just last year, the Dr. Nishimura group has shown that collagen 17A1 proteolysis and DNA damage cause the aging process of stem cell becoming naturalization. And a couple of years ago, I have found out the environmental factors, including the inhibitors, VMP, DKK, and SRP4 are upregulated in the aging mice, which is the inhibitor activate during the process of regeneration. And also, if I find out that this activator called prostatin, they can induce hair regeneration. I think that activator and also downregulate in the aging mice. So we kind of, the aging process is that the physiological regulation is the same, but environmental, there's a problem is that stem cell become aging because of proteolysis for collagen 17A1 and environmental factor of alters. For example, the inhibitor activated and the activator downregulated. That's a problem that the hair cannot regenerate very well and go into aging or hair sparse. So we propose some kind of things that cause multi-layer environmental regulation. The stem cells is not alone. They are surrounded by intrafollicle, extrafollicle. Intrafollicle, there's a niche, and extrafollicle, there are a lot of things to control it, like adipose tissue, immune system, nerve system, aging process, and the systemic factor, and also circadian rhythm and seasonal change. It also affect our hair stem cell or hair the regeneration process. So I think ideally, maybe in the future, we can go somewhere like focus on these two parts, intrafollicular or extrafollicular. Maybe we can identify some activator or inhibitors. We just suppress the inhibitors and overexpress activators to activate the stem cells. And also we can use the epigenetic way or to identify what kind of cell gene was regulated by this way to regrow our hair back. So I'm wondering, based on those studies, is there any kind of more efficient way to induce hair regeneration? That's what I'm thinking. So when I go to John's lab, initially I focus on aging, but accidentally I pluck the hair and find out that when we topologically pluck hair with some kind of randomly and efficient, proportionally to pluck the hair, we can grow 5 times more hair regenerate when properly stimuli are delivered. That's accidentally happens. That we can find out that hair can regrow back. Even we just pluck a few hair, but we can regenerate all the hair back. This is very efficient hair regeneration. It's a threshold dependent. When we give it a threshold above the threshold, when we deliver enough signals, we can simultaneously activate all the hair follicles. But whenever the stimulation is lesser than the threshold, nothing will happen. This is all non-threshold dependent regeneration, and we call this called quantum sensing. Quantum sensing is kind of situation that's a decision-making process that when all the things collect together, when the signal reach the threshold, then they simultaneously regenerate. So this process is a very efficient regeneration, and also they comes from 2-step immunoresponse cascades. So this kind of situation, can it happen in reality? That's what I'm thinking. We pluck hair, maybe we have to pluck a hair. But is that possible? I'm thinking about, is that possible? We don't really have to pluck a hair. That's mechanical force. We just have to pull the hair, but it depends on how hard I pull the hair. So it's hard to measure how hard I pull the hair. So I designed some kind of strange device of this. Okay, this is what I designed, like a frame. There's a ear over here. I can pull the skin. When I stick on the skin and pull it every day, we can get a stretch. Like I pull in the hair. Of course, not pull every hair. We just just stretch this area. This is a control mice. It's a pulling device. We can see that it really can grow hair very well, earlier compared to the control. And also, we want to know if they really have threshold, as I mentioned before. There's a threshold to induce hair regeneration. So we identify that if we pull the times lesser, nothing happens. If we pull the times too long, the regeneration will not very well. But when the duration is a lot, around 7 days, I think that's the ideal time that can stimulate all the hair back. We ignore this part because we stick here, so that's because of trauma-induced regeneration, so we ignore this part. We only observe the center, where we can see that it can regenerate very well, simultaneously, totally all around the stretch area. And also, we want to know intensity will alter. In the pulse, we track the time. Is the time really altered? Yes, affected. And also the strength. The strength really altered. If we strain only 20% of energy, then nothing happens. Strength more than 33%, I think we can grow hair very well. So I think the duration and also the intensity of how we strain, how we pull the device is very important. And also we check the time. If we traction every day, every other day, or every 3 days, it really has that kind of threshold that if we increase the strain, and every other day it can be regenerated very well. We don't have to traction every day. And also, but if we don't stretch too often, that regeneration will not occur either. So I think the threshold really occurs in here. So what happens after stretch? We kind of think about activation. So after we stretch a couple days, we follow the cells, we follow the sections, we find out that after a couple days later, stem cells start to activate it, and during the 3 to 7 days during this period. So that's now we know that when we stretch it, we really activate the stem cells. And so, because in the last paper, we showed that macrophages may involve in this process. So in this time, we just studying some of macrophages, and they find out that macrophages really activate after stretch, even from the day 1. And through all the way regenerate, they all go all over the macrophages around this process. And also, they have some dynamic macrophages response to the stretch. We isolate these stem cells, the macrophages, like markers, and always also show how many diversity of these macrophages. We also using different kind of markers to see, compare to telogen, that there's no much macrophages activated. We can find out that when we stretch like this way, macrophages through all the time, we have activated of the macrophages. And because that last time the paper published in the Current Sensing, we showed that CCL2 might be the key role to attract the macrophages around the stimulated or the trauma area. So we find out we're using a CCL2 knockout mice to see if really in this process, the CCL2 play an important role in this regeneration process. So we find out that CCL2 seems not the key regulator to attract the macrophages around, because we can see after we trash the CCL2, I did not show the mouse picture, they still can grow hair well, and also after we're using CCL2 knockout mice to stretch, we still can see a lot of macrophages around this stretch area. So I think CCL2 might not the important character during this process. And so we kind of doing some RNA-seq after this kind of process. We want to find out if any kind of genes are involved in this process. I think immune response, of course, we can see a lot of macrophages around. I think immune response is the most highly upregulated during the process, and also the hair follicle development. I think in this kind of things, we think immune system very important during this process. We also find out not only immune response, and also some kind of filigram on the cytoskeleton downregulate. I think that's, we can imagine that the mechanical force when we traction the F-actin or G-actin or that kind of cytoskeleton filament, they are dissociated apart. Maybe this information shows us that the dissociation or the did not connect very well with the stem cell, or the keratinocyte might be involved in this very important process during the regeneration. So, of course, hair cycles are also involved here. So, kind of we using some kind of chemical elimination, like chlorine, to eliminate the macrophages. We find out when we delete the macrophages, we find out that the hair regeneration cannot achieve. So, which means that really macrophages involved in this process, and when we eliminate this kind of cells, we cannot regenerate, or this kind of regeneration cannot occur. We calculate when we inject chlorine to eliminate the macrophages, we find out that when we really eliminate, we do this process, we really eliminate all the macrophages, most of the macrophages. So if the macrophage is not enough to the process, it cannot infiltrate in the whole area. This regeneration will not occur. And microRNA-seq, we do that. We find out there are a couple microRNA are regulated during the process, and we find out all these microRNA are regulated, are involved in the macrophage's fate transition. Not a lot of microRNA are upregulated and downregulated, but we find out they are very important during the myeloid lineage commitment. So which means that I think during this process, macrophage lineage commitment change may be involved, or M1, M2 transition or something. I think in this process, we find out all these microRNA are involved. Only these couple microRNA involved in this process. So I think in this process, we told it that the macrophage, during the trash problem, we still can regenerate hair well, but it's through the macrophages. How about the mention I showed in crown sensing before? Is that possible we do it in reality? In the past, I showed I using plucked hair to regenerate hair. But in reality, after I publish the hair, publish the paper, a lot of patients come to my clinic ask me to pluck hair, to grow hair. That's a problem. So a lot of patients will ask me to pluck hair. So hair plucking is not ideal. That's the concept, not really with that pluck hair. And that through that paper, I pluck more than 10,000 hairs, so kill my eyes. Dr. Chong is not here, so I can say that. So I got a severe myopia now, but if in reality, is that problem that we can do it without using hair plucking? Okay, we are dermatologists, so we have device. We have device called laser. In the past, we ablate our skin using laser, that ablative skin. We ablate all the skin, we regenerate. We call the facial, we can resurfacing to using acne scar or something, but that will cause a lot of wound there. So nowadays, we're using fractional laser, right? We're using ablative, non-ablative, we're using fractional laser. The fractional laser is a concept like our crown sensing. We don't destroy everything. We just destroy selectively. So after emit the fractional laser, depends on how many density we set or something, we can using different kind of tiny spot, that's an injury. We can diverse these kind of things to very density or low density, high density. We can do it by setting. So I design kind of things that we emit the laser on the mice with different density, different concept, with different energy or something to see which combination if the crown sensing can occur in reality. So we can see that really have threshold that we emit only 10%. This is a basic requirement. We emit only 10% of density. We can regenerate cell very well. We emit only 1 centimeter square. We can see the regenerate 1 centimeter square very well, and simultaneously we only damage 10% of the skin, and we can regenerate everything back. And these kind of things that did not reach the threshold, nothing happens. So when threshold reached, they can regenerate simultaneously, and when the threshold did not reach, nothing happens. And this is borderline, so he cannot reach, sometimes cannot. It's a borderline threshold for this regeneration. We can see the regeneration is simultaneous totally, that the hair regeneration back, whole area we emit in the 1 centimeter square without damaging skin. So we think that's kind of things we can use in reality when we do it. Interesting thing is that when we do this kind of situation, we find out that when we eliminate the proper density and proper energy, we really can activate the stem cells after we do the cell. Doing the process of laser, a couple of days later, we can find out the stem cell really activate. But if we eliminate this kind of low density, this kind of low energy, nothing will happen. So only the proper density and the proper energy can emit, or can have this kind of result. Interesting thing is that we can see left-hand side is the area we emit the laser. Right-hand side, nothing happens. It's outside the area we emit the laser. We can see if we're using the proper density and the energy, the macrophage migrate to the area we did not emit. That's why the crown sensing occurs, that all area can regenerate simultaneously. This is low energy, this is low density, this is low energy. The macrophage will not migrate. That's why nothing happens. The regeneration cannot occur. I think that's the concept, as we said, when the proper density or energy will reach the threshold, the regeneration will occur. So we kind of doing the elimination, as I showed you before, we using quadronate to inject in the back of the mice skin. We can see very nicely, very beautiful 1 centimeter square here. We inject the macrophage inhibitor, really escape this area to regenerate. So we can see very beautiful data to show that when we eliminate, to delete the macrophages, the regeneration can occur very well, but cannot regenerate here. So when minor injury occurs, I think we kind of summary that the regeneration is still not that easy. So it's combined with intrafollicle, extrafollicle, every kind of cell contribute to these things, including adipocytes, including macrophages, including some kind of fibroblasts or adipoprogenic cells or something. I think that's kind of idea that regeneration is not that easy just inside the follicle, but outside the follicle is more important to regulate these things. So in conclusion, the summary that stem cell regulation is complex work. Macrophage involvement in this process very well, and also I think quantum sensing is the kind of concept that can stimulate the regeneration very efficiently, and we want the regeneration wound healing, not repair. Because for repair, we leave the scar. We hope the regeneration wound repair will be come through in the future, and we hope by manipulate the environment, not just stem cell is enough to trigger all the regeneration response. So I want to thank the mentor, Dr. Chen and Dr. White here, and also the collaborators, and also our support by the NIH, our grant, not NIH, the Ministry of Science Technology in Taiwan, and also we hope we can enjoy this meeting and have the hair growth back. Thank you very much.
Thank you for a fascinating presentation.
Thank you.
Any questions?
Thank you for the talk. I have two questions. One is on the tension model you created on mice. Have you done an estimation how that feels on human, the tension you have to create? Second question is, have you considered to isolate the tissue resident macrophages after your tension creation and see if that can transfer to the other mice and create regeneration?
That's a good question. First of all, in human, yeah, I try now because we have IRB regulations. I did not have time to show data. I have some data for the razor for human. For the traction device, we still have no device to do that. I think we can design the device to do that first. The second question is that yes, I have done that. We have no time to show that actually the macrophage is not just macrophage there. They do a lot of things, a lot of cytokines, a lot of growth factors. We isolate the stem cells. We isolate the macrophage by sorting. We inject to the other mice. Yes, they can regenerate well. And also, but by some conditioning, we sorting that kind of cell. And also, if we don't sort the cell, we can differentiate the bone marrow from differentiate the macrophage from bone marrow. We do the bone marrow to differentiate to specific lineage of macrophage. They still can regenerate hair. So I think the specific subtypes of macrophage is involved in this process. Thank you.
I thought it was super interesting. I have a couple of talks. Firstly, if we use this device, do we not have to leave the EU? Was my first question with regards to Brexit.
Sorry, I not get it. Sorry, can you?
It's a joke.
Yeah, okay.
Anyway, it didn't go down so well.
And
secondly, it seems a bit counterintuitive to me. When you have a wound, if you apply too much tension, you get a bigger scar.
Yes.
But here you're applying
Yes.
tension and you're creating a regenerative rather than a
Yes.
repair process.
Yes.
So I wondered if you could comment on that. And then secondly, it seemed that your device was stretching along the anterior to posterior
Yes.
axis, and I wondered if you stretch in
Yes.
another direction,
Yes.
do you get a different effect?
Yes, that's wonderful questions. Yes, we have asked about that. You can see the tension, if we stretch too much, nothing happens, as you said, the scar formation. So I think the balance is very important. As I said, we show the TNF-alpha induced regeneration. As the last day, I saw that from China, they also seen TNF-alpha. But actually, we deliver too many TNF-alpha scar formation, yes. So I think much information, I think minor information stimulate regeneration, but much information, I think causes the damage of tissue. I believe you are right. So that's why when we tension, we did not pull much. If you pull much, they will get a scar, yes. So according to the second questions you mentioned about, yes, the way that we have shown, we want to do that, but it's hard. You know, the device will fall because the mice will struggling to do that. I don't want to wear some kind of things on the back. So I think when we pull this size, they fall every day. We cannot fix it very well, and because we want to stick the size with 1 centimeter in the first, then we pull it. But the mouse, the diameter is this long, so it's easier to play this way. But this way, we cannot. The tension will release when it's back. We will tend to pull it. So that's why every day we got to pull it again. But for this area, for the widest, we cannot pull it in this side, this direction. So we hope we can design another device to do that. Thank you. Hey.
Hi, I really enjoyed your talk. I was interested in your collagenate experiments. It's been shown that collagenate can have massive hair cycle delays. So I was wondering how you could comment on how that might affect your hair regrowth measurements.
Excuse me, what kind of
So if you inject with clodronate, it was shown
Oh,
a few years
yes.
ago that this can affect the hair cycle progression in mice.
Yes.
So I wonder how that may affect your hair growth
Oh,
results.
okay. I think that's clodronate just so we got to do that before the macrophage are proliferated. So we arrange that kind of a study by inject the subcutaneous or peritoneally. So we're using either way, but in fact, actually we have done that. If we inject too many clodronate, the mice cannot survive well, and so we decide to do that. So we inject before the macrophage eliminate. So we do the device. We arrange the device before we do the process. We inject that, and then we continue to inject every other day or something to maintain that macrophage cannot proliferate well. Did that answer your questions?
Kind of, not really.
Okay, really?
Not really.
Okay.
We've got time for one last question.
Thank you, very great talk.
Yes, thank you.
Maybe I would like to know more, but have you tried to check that with aging?
Yes. That's quite good questions. Yeah, we want to try now because in Taiwan it's hard to purchase aging mice. In America we know I purchased an NIH, but in Taiwan I had to raise them until they are old. So I wait for 2 years to do that kind of study one time. So yeah, I will do it. Yeah, the mice is getting old. Yeah, now, but we will do it now. So that's a problem. Yeah. So in my lab, the mice study they survive very well. They can survive there without anything, eating and drinking, and then for 2 years. So that's good. That's right.
Okay, thank you very much. We better move on to the next speaker. Thank you very much for that presentation.
Thank you.